Okay, moving on through lecture notes 2, let's talk about skewness, kurtosis, correlation, etc. What is skewness? All right, we've introduced the expected value, the variance. The expected value has no powers in it, so it's whoops. Apologize about that. So let's remind ourselves what the expected value is. Expected value is just, that's our formula there, also defined as mu of x. The variance of x, is going to be expected value of x minus its mean squared. So the variance has a squared term. The skewness is just, we're going to add a cubed term. And to standardize it, we're going to divide by this bit here. The skewness is a measure of the asymmetry of a distribution. A skewness of equal to 0 is a symmetric distribution. So let me draw some kind of example of that here. So if I had if I had a perfect hand, this would be a perfectly symmetric distribution. I don't have a perfect hand, so it's not perfectly symmetric, but let me draw something that's obviously not symmetric. There we go. There's more mass out here on the right than there is on the left. So this would be, over here, this is an example of a non-skewed distribution, or skewness equal to 0. On the right, we have a skewed distribution. Kurtosis is a measure of the mass in the tails, or the probability of large values. Kurtosis equal to 3. Okay, so we should remind ourselves we're jumping up a power here. The kurtosis equal to 3 is a normal distribution. Kurtosis greater than 3 is heavy tails. So this is basically getting at, okay, here we have a normal distribution. Now is it, how much mass is in these tails? Well, we talk about the tails, we're talking about these bits over here, in here. How much mass is in the tails? What do we mean by mass? This area here. How fat are the tails? So this might be a normal distribution, what I've drawn. One that has a little more mass than the tails. Let me exaggerate this a bit. Might look like this. So there's a lot more mass in these tails. A joint distribution. This is just a definition. The joint distribution is the probability that two random variables simultaneously take on certain values. We write it, the probability that the random variable x is equal to the outcome little x. At the same time, the random variable y is equal to outcome little y. Properties, probabilities of all possible xy combinations sum to 1. This might be the probability that you rode your bike to school and you ran over some glass, and then that might be the probability of y. And the probability of x might be you got a flat tire. So these are two random variables. A conditional distribution. Again, we're going to introduce this concept. It's the distribution of a random variable y taking on a certain value y given or conditional on another random variable x taking on a certain value x. And we write it like this. So this bar here means conditional. It's slightly different than the joint distribution where we're adding a comma. That leads us to the conditional expectation. It's the same as a regular expectation, I should say expected value, except now we look for the average of a random variable, conditional on another random variable taking on a certain value. All right, and so we write it as the expected value of y, conditional on x equals little x taking on some value. And the formula is the sum of I equals 1 to k of all possible outcomes for yi. Notice we're taking the average over y, not x, and so we get yi here times its conditional probability here. So an example of this would be the expected value of wages for female workers. And we could write that expected value of wages conditional on this variable female is equal to 1. This is different than, if we wanted to find out what's the average wage amongst all workers, that would be a different outcome than the average wage for just female. All right, independence and covariance. Another definition, independence is two random variables are independent or independently distributed if knowing the outcome of one random variable provides no information about the outcome of the other. In other words, the probability that y is equal to little outcome y conditional on x equals little outcome x is equal to the probability that y is equal to little outcome y. In other words, knowing this does not help us at all about if we want to know that. Covariance, a measure of how two random variables move together. The covariance is defined as, we write it covariance xy, so two random variables x and y. Their covariance is going to be written as this. By definition, it's the expected value of x minus its mean times y minus its mean. The interpretation is when x tends to be greater than its mean and y tends to be greater than its mean, the two variables will be positively correlated. If x tends and y tend to move in opposite directions, then they're negatively correlated, and when x and y are independent, then the covariance is 0. Properties of covariance. All right, if we have two random variables x1 and x2 times two constants a and c, then we can just take those constants out, like that. Number 2, adding a constant to a random variable does nothing to the covariance. That's this here. You're basically adding an intercept to each of the random variables. Number 3, we can take these properties and put them together. So now we're just taking 1 and 2, putting them together, and we can take out the constants that are multiplied and just drop the ones that are added. Here's a nice one, number 4. The covariance of x2 and x1 is equal to the covariance of x1 and x2, meaning that it doesn't matter which way we put these into our formula. And then finally, the covariance of x1 with itself is just the variance of x1. We can write this out as, if we take the covariance of x1 and x1, is equal to expected value of x1 minus its mean times x1 minus its mean, which is equal to expected value of x1 minus its mean squared, which is equal to sigma squared x, or in other words, the variance of x. The correlation, this is a nice one, it's the standardized covariance. We standardize the covariance because the units of covariance are difficult to interpret. The units of the covariance are in really the units of the variables that you're defining the covariance over. The correlation is nice because it has very standardized properties. So to get the correlation, we write covariance over the variance of x times the variance of y and the square root of all that, and we can write it as this. The properties of correlation. Correlation is always between -1 and 1. Correlation of 1 is perfectly collinear. Positive correlation is greater than 0. Negative correlation is less than 0. Let's draw some correlations. Okay, if we have, let me see if I can make this a bit fatter. Great. Suppose that we have two random variables. This is y. This is x. What is the correlation and if this is our scatter plot? Well, I can't really draw an obvious line through here. I meant to draw this as sort of a cloud, so I would call this correlation approximately equal to 0. What if I draw one that looks like this? Okay, so now we have two random variables x and y. suppose we drew the scatter plot and it looked like that. I can draw, I can now see some sort of relationship here. I can draw a line that goes like that. So now I would say the correlation between x and y is greater than 0. It's positive correlation. Not necessarily 1. Correlation of 1 would be a line. This is just some positive correlation. This is pretty high correlation though. Let's do one more. We have our variables x and y. Now we'll get something that looks like this. We can see that we can kind of draw a line that goes like that. So the correlation here is going to be less than 0. Negative correlation. Okay, what if I give you this? Here's kind of a trick question. And this is sort of a teaser for the rest of the course. Okay, there's obviously correlation between these two variables, but it's not negative, because if I draw the negative line, it goes like that. It's not positive, because if I draw the positive line, it goes like that. So it's quadratic. But if you estimated the correlation between these two variables, it would probably give you 0, or something close to 0.